Hello, this is my lab report for Lab 3. So the purpose of this lab was to use Python code to analyze a star's motion that is orbiting a black hole with unknown mass, and the trajectory of the star is unique to my email address. And then I used Newton's second law and the dynamics of curving motion to find this unknown mass for the black hole. So the first physics principle that I used was Newton's second law, which says that the net force is equal to dp over dt, which is the change in momentum over the change in time, and momentum is mass times velocity. And then the gravitational force is going to be equal to that because that is the force that is acting on the star. And then the net force is made up of the parallel component and the perpendicular component, and the formula for the parallel component is the change in the magnitude of the momentum over the change in time times the unit vector for momentum. And even though there's a formula for the perpendicular net force, I don't actually need that because I can just subtract the parallel component from the net force. And then finally I have this formula which says that the magnitude of the gravitational force is equal to the gravitational constant times the mass of the star times the mass of the black hole over the magnitude of the distance of the star and the black hole squared. And then some of the data values that I'm going to be using is the mass of the star, which was given, a delta t, which is the time between the data points, which is going to be 1 day, or in SI units 86,400 seconds. The time of the first observation, which is just 0 seconds. The position of the black hole, which is at the origin, and then the length of the arrow showing the net force, and the parallel and perpendicular components is just 10 to the power of negative 17. So in the code, I have my email address that determines the trajectory of the star. I have these data values, the gravitational constant, the mass of the star, the time interval delta t, and the time of the first observation. And then here is where that Newton's second law comes in, which says that the net force is equal to delta p over delta t, with delta p being the change in the momentum. And then here is where that formula for the parallel component of the net force is. And then I just subtracted that parallel component from the net force in order to find the perpendicular component. And then here, this comes from this formula, but I just moved everything but the mass of the black hole to the other side so that I can find that unknown value. And because the position of the black hole is just at the origin, the distance will just be equal to the position of the star. And then the gravitational force was just the F net. So when I run the program, this is what it looks like. There's an elliptical orbit around the black hole, and the orange arrow is the net force, which is always pointing at the black hole. And then there's the magenta arrow, which was the perpendicular component, and then the parallel component, and then the perpendicular component is that teal arrow. And then here are the final values I get for those. And then for that unknown mass that I was trying to find, I have all the code has all these data points, which are slightly different. And so when I average them up, I got 1.93 times 10 to the power of 34. So the what does it mean question, which was what is the difference between the net force and the rate of change of momentum and its parallel and perpendicular components. So you can see and observe changes in momentum while the net force is the actual push or pull that is applied to the object to cause a change in momentum, which cannot be seen. And then if the black hole was removed and a new one was put in its place, but the star's trajectory was the same, we wouldn't be able to see a difference in mass because the gravitational force is still going to be the same and the trajectory path is not going to change either. So, thank you.